Here we're going to talk about substitution reactions and reaction pathways. This is going to center on halogenoalkanes. Okay, we're going to see that there's basically two different mechanisms that we're going to talk about. One having to do with primary halogenoalkanes, and the other having to do with tertiary. And then we will mention secondary. Okay. So let's talk first about the substitution reaction when we are dealing with halogenoalkanes. Halogenoalkane really just means that I have a chain and carbon, and somewhere I've got a halogen attached to it. Okay, and this hopefully you recognize. If I had to ask you, it's hard to write those up there. Have to ask you whether this was a primary, secondary, tertiary. Hopefully you can look at this carbon, see that it has one alkyl group, two hydrogens. This would be a primary halogenoalkane. All right, so let's talk a little bit about the structure of these. This is a polar bond, all right, greater electronegativity on the bromine, pulling the electron cloud this way, okay, compared with this carbon-to-carbon bond. So what happens with this polar bond is this carbon atom, I'm switching down here, okay, this carbon atom has a partially positive charge. There will be a reactant known as a nucleophile. These are attracted to the positive charge. So these nucleophiles with this unshared electron pair are going to be attracted to this carbon. Okay. So they're going to come in and kind of push this bromine out and make a new bond with this carbon. So reagents with a non-bonding pair of electrons are nucleophiles. They're attracted to that positive charge. So they come in and kind of force that bromine out. That's overall quick summary of what happens. Now we're going to take a one thing, oops, don't look, oh, went the wrong way. Common nucleophiles you should be aware of: water, the hydroxide ion, ammonia, and the cyanide ion. These are all nucleophiles that you should be familiar with. Oops. So let's look at this mechanism in a little bit more detail. Okay, again, primary halogenoalkane, one alkyl group attached to the carbon, which is attached to the halogen. So we're looking at something like a chain here. This is what's drawn here. I think it's kind of weird this arrow goes there. Don't copy this down the way it's written. Write it. Getting ahead of myself. Ready? If we look at the equation, it's a rough day. If we look at this equation, okay, I have my halogenoalkane, my nucleophile, in this case hydroxide ion, substituting the hydroxide ion for this bromine, I end up with the alcohol and a bromide ion. Experimentally, it was determined that the rate was equal to the, I should say proportional to the concentration of the halogenoalkane and the hydroxide. So if you remember, this has a reaction order of 2. It is also called bimolecular. throwing a little bit of kinetics in there. Proposed mechanism, okay, involves the formation of a transition state. How does this transition state form? This hydroxyl group with its unshared electron pair is attracted, and I kind of would draw it more to the electron deficient carbon. It's partial positively charged carbon. The bonded electrons that are between this carbon and the bromine are going to move to the bromine itself. So this electronegative bromide ion is going to attract those two and kind of take both of these electrons in this bond. The nucleophile with its unshared pair of electrons is going to donate those two bonds. If you remember, that's called a coordinate covalent or a dative bond. Okay, he's going to donate both of them. This reaction forms an intermediate or a transition state where I have the hydroxide bonded and the bromide ion bonded. Everything else kind of just hangs out there. It has a transition, or it has a negative charge for this transition state. When the reaction is complete, my hydroxyl group has taken the place of this bromine. Okay, and the bromide ion is free. Okay, the molecularity again is 2. It is known as an SN2 mechanism. Bimolecular nucleophilic substitution is what this SN2. S, substitution, N, there's a nucleophile involved, 2, meaning it is bimolecular. So SN2, bimolecular. Important thing to note, the rate of the reaction is dependent on both of these reactants. There is a transition state formed where the nucleophile is forming the bond with the carbon, and the carbon is giving up its electron for this halogen to become an ion. These are going to happen with primary halogenoalkanes. So primary halogenoalkanes tend to react by an SN2 mechanism, a bimolecular nucleophilic substitution. Kind of opposite to these is a mechanism for the nucleophilic substitution. The nucleophilic substitution happens, and we'll look a little bit more in detail, maybe not, with my tertiary halogenoalkane will form a carbocation and a bromide ion. Then that leaves a, I guess, kind of a space for your hydroxyl ion to then form a bond with this carbon. Okay, and this second reaction happens very fast. So, two-step mechanism. If you notice, this is your slow step, so your kinetics are based on this slow step. The only reactant I have is my halogenoalkane. It is then a first order, so it is unimolecular. Its mechanism is known as an SN1, unimolecular substitution nucleophilic. Right? So S with a subscript capital N and a 1. This happens with tertiary. Now, I want to just look at it in a little bit more detail. If we draw that tertiary halogenoalkane, let's say I have a bromine. Right. And this will happen slowly. The curly arrows showing the movement of the electrons. The electron pair moves to this bromine. Okay. They are a polar bond. Carbon gives these up. What happens actually is because I have these bonds, okay, and they're carbons or chains, they kind of stabilize this movement of this electron from this carbon giving up its electrons to this bromine. And it adds a certain stability of that. So that when I do form this carbocation, with this little plus charge here, it's the ability of these electron clouds to kind of not make this a full positive. It's a full positive overall because carbon has given up its electrons, but the electron clouds of these alkyl groups kind of give up some of their electrons to kind of stabilize this whole carbocation. Okay, and this is called, I'm sorry, carbocation intermediate. Oh dear. Carbocation intermediate. Now, if you think back to the previous mechanism with the primary halogenoalkane, there was the nucleophile kind of came in first and it formed this transition metal where, or this transition state where I had kind of 5 things connected to this first carbon. If you look at the structure of a tertiary, I've got all these atoms, okay, this methyl group, 3 methyl groups surrounding this carbon. There really isn't room for a nucleophile to kind of come in here and form that transition state that happens in a bimolecular nucleophilic substitution. Okay, so because of that, and it's called steric hindrance, and it's basically it's too crowded around that carbon for that nucleophile to come in. All right, so this happens with a different mechanism, this slow step forming this carbocation intermediate, and that ion, and then the fast step being the nucleophile coming in and donating its electrons to that bond, and we'll show that step real quick. So in the second step I have my carbocation with the stability of these electron clouds kind of adding stability to this whole carbocation. Then I have my nucleophile that would be coming and with the curly arrow showing where the electrons are going to go. After the reaction, I will form the alcohol. This is fast, so it's not rate determining, it's determined by the first. So then you might be wondering, well, we'll get back to this in class. So you might be wondering, what about secondary halogenoalkanes? Well, they proceed by a mixture of both the unimolecular nucleophilic substitution and the bimolecular nucleophilic substitution. Okay. Right. There are some additional notes to be taken about the nucleophilic substitutions, but we're going to pick those up in class.